In today's lesson, we're going to learn about something called the binomial distribution. Today's going to be a fairly calculator-heavy lesson, so make sure that you've got your TI-84 graphing calculator nearby. The TI-84 is the one that I'm going to be explaining the instructions for. So before we get started, let's go ahead and take a deep breath. And let's begin. So in the past couple of lessons, we've talked about a probability distribution, and so I sort of want you to recall or remember a probability distribution is just a table or a formula or a rule that specifies the probabilities of some random variable. Now, in this class, we're actually going to learn about two different named distributions, which means very, very specific distributions that have specific purposes. One of them is called the binomial distribution. That's what we're learning about today. And the other is called the normal distribution, which we'll be learning about sometime later in the year. Turns out there's actually a lot of different named distributions. And if you're interested in exploring other probability distributions for your math IA, your math exploration, there are a lot more of them. Two of them that may be sort of accessible are the Poisson distribution and the hypergeometric distribution. So heads up, there's lots of these things. Today we're going to be learning about the binomial distribution. As is the case with many lessons on new things, we often need to start with vocabulary. Math a lot of times revolves around the vocabulary that's defined and the sort of the starting point that we have. So in this case, in order to understand what a binomial distribution is, we need to understand what a binomial trial is. Now, we've seen the word trial before. We know that a trial is basically a thing that we do or an experiment that has some sort of measurable outcome. So a binomial trial is a trial or an experiment that can be considered to have two outcomes. So this binomial is indicating that it has two outcomes, and those are generally referred to as success or failure. So one of the easiest binomial trials to think about is flipping a coin, right? Flipping a coin realistically has two outcomes. It's either heads or it's tails. In this case, those are sort of evenly weighted things. For a binomial trial, it doesn't have to be something that's 50-50. But the first example that I gave was. Another example of binomial trial could be rolling a die. Now, you may be thinking, but a die has 6 sides. That's true, but if you rolled a die and you were looking at 5 versus not 5, now that's binomial. Either you succeed, you got a 5, or you failed and you didn't get a 5. Another example of rolling a die could be getting odd versus even. Again, I mentioned that sometimes the probabilities are the same and it's 50-50, and other times it's not, right? So again, the key thing behind binomial trial is that it's a trial or an experiment that has two outcomes. Right? The last little mini example that I have here is the idea of the weather, right? The weather could be a binomial trial, right? If you go out and sort of measure the high temperature for the day, you could think about the temperature being above 80 versus the temperature being 80 or below, where you could take a large thing and break it down to sort of two cases. So now that we know what a binomial trial is, a trial or an experiment with two outcomes, the binomial distribution is a probability distribution that allows us to compute the probability of obtaining a certain number of successes on some specific number of binomial trials. So if you rolled a die 10 times and wanted to know what the probability of getting 3 5s was, that would be an example of a problem that you would solve using the binomial distribution. So next, I'd like to take a closer look at what one of these binomial distribution problems might look like. We're not actually going to solve it right now, but I want to break down the pieces of this thing so you can sort of see what it is that makes it binomial and you can see the stuff that's here. So we will solve this problem in a couple minutes, but right now we're just going to sort of break it apart. So this example says a fair 6-sided die is rolled 10 times. What is the probability of obtaining a 6 exactly 2 times? So there's 3 important pieces of information here. Right? The first one is how many binomial trials were there? Okay, so in this problem, how many times am I doing this binomial trial? The binomial trial being rolling the die and obtaining this 6. So hopefully you guys saw that the number of trials that there were is 10. This is often called n. So in this case, we're going to say n is 10 because I'm carrying out this trial 10 times. Next, what are we counting as a success? And what is the probability of individually getting that success? Well, what we're considering a success here is rolling a 6. Okay, so next part of this then. So what is the probability of individual success? So not what's the probability of getting 2 of them, but what's just the probability of getting a 6 on this fair 6-sided die? You You guys hopefully recognize this is 1/6. We're generally going to call that P, right? P, the probability of getting a 6 is 1/6. And finally, how many of these successes do we want? Okay, well, the problem said that we wanted to get the 6 exactly 2 times. Okay, so that means I want this thing to happen 2 times. This is either called r equals 2 or sometimes it's called x equals 2 depending on the book. So when you're working through these binomial distribution problems, you're going to need to find out how many trials, what the probability of individual success is, and then how many successes you're looking for. So we're going to take this information and then move forward and talk about how we're going to show our work for problems like these. So next, I want to talk about how we show our work for these problems. And this slide is really, really important. These steps are important for this problem, but they're also important for some of the work that we're going to do later on as we move through probability. So starting in 2021, as far as I can tell, and no one's seen the new exam yet, but my sense from what I see is that I don't think that the IB exam is going to require you to know or be able to use the formula for finding binomial probability. We may need to teach it at some point, but I'd also potentially like to leave that open as an IA exploration topic for somebody. All of your computation for this stuff is going to be done on the calculator. And so we're going to use these following steps or method as a way of showing our work and understanding a problem. Because like IB, you can't just write on the exam like, I did it on my calculator, and then write down the answer and expect to get full credit for it. You need to sort of show what your reasoning is. Okay, so there are going to be these 5 steps, and we're going to do several problems here to practice this. So step 1, in these problems, you need to clearly define your random variable. Okay, your definition should start with something like let, and then you pick the random variable you're using. Let x be the number of 6s that you roll, or let x be the number of days where the temperature was hot, or let x be the number of tails. So you're sort of defining the variable. You want to include the capital letter that you're using to designate that random variable, and you want to clearly indicate the number of trials and what you're counting. So you're sort of lining out all the stuff. And again, we're going to get plenty of chance to practice that in this video. Step 2, we want to use proper mathematical notation to indicate that the variable is being distributed binomially. And again, in the next example, I'll show you exactly what that looks like. Step 3, you're going to use proper mathematical notation to indicate clearly the probability that you're trying to find. So at that point, you're going to bring in the number of successes that you want. Step 4, for more complicated problems, you may need to rewrite step 3. And then in step 5, you're going to use your calculator to compute the probability. So at this point, I can't put the calculator screen up on this video, but I want to sort of write down where you're going to find the calculator stuff for this. So on your TI-84 calculator or similar calculator, what you're going to do is you're going to hit second, and then there's a distor button for distribution, and it's right above vars. It's right by the arrow keys, kind of in the upper right. So you'll hit second, distor, and then within that distribution menu, if you go almost all the way down to the bottom, you'll see 2 functions there. One of them says binom PDF, and the other says binom CDF. Okay, and those are the functions that we're going to use for these things. I'm going to go ahead and mention one more thing. When you hit those, the next screen that you get to asks you for trials, it asks you for P, and it asks you for an X value. And my bet is that you can kind of guess what those things are going to be, right? Trials is where you're going to put in N, the number of trials that you do. P is where you're going to put in the probability of individual success. And X value is where you're going to put in sort of, either X or R. This is going to sort of be those number of successes that you wanted to have. There's some complexity there. We're going to come back to it. But this is sort of like this 5-step process is what we're going to write down to get full credit on these problems. And I expect you guys to do these for all of these binomial problems that we do. It doesn't actually take that long, and it's a good habit to get into. So now we're going to come back to that problem that we had a couple minutes ago that we didn't solve. We just kind of talked about why it was binomial. So a fair 6-sided die is rolled 10 times. What's the probability of obtaining a 6 exactly 2 times? So step 1, we're supposed to define the variable. Right? Remember from the previous slide, we're supposed to start with this like, let x be the number of, and we write the thing out. So I'm going to go ahead and show you here what that should look like. So So I write something like, let D, I'd use D for die, let D be the number of times a fair six-sided die comes up 6 when rolled 10 times. So notice I defined the variable, I said what I was counting, I said the number of sixes, and I put in the number of trials, 10. Okay. Now that we've done that, we need to indicate the distribution. In other words, we need to tell the IB examiners, we need to tell the grader that you know that this is a binomial problem. And so this is the notation. We write the random variable D, and then we use this, kind of tilde notation, this like squiggle, which means is distributed. We write a capital B for binomial, and then we put in parentheses 10 for the number of trials, and then we put the probability of individual success, 1/6. Okay. Now I know that's a whole lot of new notation, so I'm going to slow down here for just a moment and make sure that you got that. When you're saying that something is distributed binomially, you're going to say D, the variable you chose, D is distributed binomially with 10 trials and an individual probability of success, 1/6. So there we go. I sort of wrote out how we would read that or what that means. So first we define the variable, then we indicate the distribution. Then I want to state the probability, indicate the probability that I'm trying to find, right? I want the probability that my random variable D is, and what do I want? If D is the number of times a fair six-sided die, fair six-sided die comes up 6, what do I want D to be? Well, I wanted exactly 2 successes, so D being 2. Now in step 4, we don't need to rewrite. I'm going to come back to that one later, so let's not worry about that. Now in step 5, we want to compute it. At this point, the calculator does literally all of the work for us. Okay, so at this point, we can plug into the calculator binom PDF. So go back to that dister menu and then go down to binom PDF. And then it'll ask you about trials and P and the X value. And now that we have all this stuff, we tell them, yep, there were 10 trials, individual probability of success of 1/6, and we wanted to use an X value of 2. When you put all that stuff into your calculator, it'll paste it back to the home screen. So then your home screen says this. And then if you hit enter one more time, it comes back and tells you 0.291. So there's this like 29% chance that we're going to get 2 6s when I roll a die 10 times. I want to point out really quickly, by the way, for the purposes of the IB exam, this and this do not need to be written down. IB doesn't want to see calculator speak. They won't take off points, but they're not like this does not show work. IB will not give you any credit for that. This maybe, but honestly, all of this information is already stored up here, right? So what IB really wants to see is they want to see the definition of the variable, the distribution, the probability, and the answer. They know you're going to use a calculator. So this is sort of what the work looks like on these problems. This stuff up here is where you get partial credit. This is where you get your answer. The entire rest of this video is just examples of this and us practicing it. So let's dive right into this next one. And I want you to remember to think about those 5 steps for each one of these things. We want to be doing those 5 steps. A student is late to first period class 13% of the time. In a 5-day school week, find the probability that the student is late to class exactly once. So if you're up for it, try this one on your own. If you want to see one more, there's going to be more examples that you'll be able to do on your own. So step 1, we're supposed to define our random variable. Right? So my random variable here, what I'm counting is the number of days that they're late. So maybe I'm going to use L. So there it is. Notice what I did. I used the word let. I picked a capital letter. I mentioned what I was counting, the number of days. I mentioned the number of trials, how many days, and then I just sort of described what it was that I was going to be counting. Great. Step 2, I'm supposed to state the distribution. So here, I'm going to say that L is distributed binomially. There are 5 trials because I'm looking at over a 5-day week. And the individual probability of success, by the way, success doesn't always sound successful. In this case, what we're counting is we're counting them being late to class. And so success here is being late to class. I'm not sure how I like saying that out loud, but that's going to have a 13% chance, so 0.13. Step 3, I want to write down or state or indicate the probability that I want to find. I want to find the probability that L, the number of days that they're late, is exactly 1. Okay. Step 4 we know is about rewriting these things when they're complicated. We're not at the complicated ones yet. We'll get there, so we don't need to have anything more there. And then in step 5, I really just need the answer. I'm going to sort of write out and show you one more time. I'll use red for it. I'm going to write out what IB doesn't need to see. They don't need to see you put binom PDF, parentheses, and then you'll put in that there were 5 trials, an individual probability of success of 0.13, and 1 trial. All of that is not what IB needs to see. All they want to see is that when you went through and did that and got, let's see, 5.13, 1, that this is 0.372. And that's our answer. So for these problems, literally this is the work, and this is the answer. And for the simple binomial problems, like that's all to it. I mean, that's all there is to it. So this is the last of my sort of like simple examples. Now we're going to get into ones that have a little bit more bite to them. So an economics test consists of exactly 10 multiple choice questions. Each question has 5 answers, only one of which is correct. Find the probability that a student who guesses randomly gets exactly 3 questions correct. So pause the video, try this one on your own, make sure you can get it. Step 1, we need to define the random variable. So there we go. I decided to use n. Let n be the number of questions a student gets correct on a 10-question multiple choice exam that has 5 options. These 5 options may or may not be necessary. It's nice to do it. It gives a little bit more information about the random variable. Step 2, we're supposed to state the distribution. N is distributed binomially. There are 10 trials because there are 10 questions. And with a 1 in 5 chance of getting any given thing right, well, I mean, great. We just put 1 out of 5. Step 3, I'm supposed to indicate the probability that I want to find. I want the probability that n, the number of questions correct, the probability that that is 3. Step 4, for one more slide, there's nothing I need to do to rewrite this or set it up differently. Now in step 5, remember you're going to use the binom PDF thing here. So when I go to my calculator and use binom PDF, and I put in 10 trials, individual probability of success of 1/5, and 3, I got this to be 0.201. And this is our answer for the problem. So about a 20% chance. You know, something I haven't talked about yet in this video is the concept of reasonability. Does this answer make sense? Right? And I think one of the things that I always like to do and like to think about is in a problem like how many questions should the student have expected to get correct? Right? If there were 10 questions and they have like a 1 in 5 shot of getting them right, we would probably expect them to get about 2 of them right. Okay, so the probability of them getting 3 of them right, which is kind of close to this, like feels like there should be a decent chance of that. 20% is sort of like a fair chance. If this question had said, what's the probability that somebody gets, 9 of them right, and you found that it was 20%, I hope that you'd be like, there's no way that you managed to get that many of them right by randomly guessing. Hopefully, as you do more and more of these, if you think about reasonability, you'll be able to sort of like see that. If that doesn't make sense, make sure you ask me about it, because I do think that making sure answers are reasonable is an important part of the process. So the next few problems that we're going to do have a little bit more complexity to them. I don't know if you noticed, but that last question was kind of awkward. People are generally not interested in, what's the chances I get exactly 3 of them right? You're generally interested in getting like at least some score. You don't really care about what are the chances of me getting exactly 75%? And so in this one, we're gonna sort of look at how the binomial distribution addresses that. So in this one, a chemistry test consists of exactly 20 multiple choice questions. Each question has 4 answers, only one of which is correct. Find the probability that a student who guesses randomly gets 8 or fewer questions correct. So notice that in this one, I'm not asking about exactly 8. I'm saying something like 8 or fewer questions correct. Okay? The steps we use are going to be the same. Okay, so step 1 is still going to be define the random variable. So, pause the video, make sure that you can define the random variable first. So I decided to define let C be the number of questions answered correctly on a 20-question multiple choice test with 4 answer options. Your wording doesn't need to be exactly the same. The thing that's important is you need to have a random variable defined. You need to talk about it being the number of questions answered correctly, and it needs to reference somewhere that there were 20 questions. Okay. Step 2, I need to state the distribution. Okay. C is distributed binomially. There are 20 trials, and each of those trials individually has a chance of success of 1/4. Why is it 1/4? Well, because we're counting correct answers, okay? And there are 4 answer options for each of them. Step 3. Step 3 is where we write down the probability I want to find. I want to find the probability that C, the number of correct questions, and this next step is arguably the most important step of the entire problem. The symbol that I put right here is really, really important. And you may think it's really easy. It is on this one, but we do need to take care. When I say 8 or fewer questions correct, what does that mean? Like 8 or fewer means that I got 8 correct, or I got 7 correct, or I got 6 correct, or I got 5 correct, or maybe I even got 0 correct. All right, so how would you express that then? What would we say about C? Wouldn't we say that C is less than or equal to 8? That's the kind of thing that I want to write down, okay? And the thing that gets people most is they're like, should this be greater than? Should it be less than? Should it be equal to? Should it be not? I personally will generally write down the kinds of successes that they're looking for, and then I'll pick the symbol, and then I'll double check my work. I cannot tell you how many times students, even like really bright students that tend not to make these kinds of mistakes, will put the wrong thing here, and then the rest of the problem kind of gets messed up. All right, so let's move on. Step 4, this actually still doesn't need to be simplified, and I'm going to explain why in just a moment. So now we get to step 5, okay? And in step 5, I need to plug this into the calculator, okay? But here's the catch. When I use Binomial PDF, like if I did Binomial PDF, and I'll put this in red, if I did Binomial PDF and put in 8 trials and 20 trials and an individual success of 1/4 and 8 for the number of successes I want, wouldn't that find me the probability of getting exactly 8 correct? I mean, I guess we could find the probability of 8 correct and 7 correct and 6 and 5 and 4 and 3 and 2 and 1 and 0 and add them all up, but that's a ton of work. That's not what we want to do. So instead, we're going to use Binomial CDF. And what that C right there stands for is it stands for cumulative. Okay? So when you use Binomial CDF, it will automatically find you all of the probabilities up to and including the value that you give. So again, Binomial CDF computes a cumulative probability. So if you put in an x value of 8, it'll find the probability of any number of successes up to and including 8. So on our calculator, if we go in and put in Binomial CDF, 20 trials, individual success of 1/4, and then 8, it will come back and tell us that this is a 95.9% chance. So this really just confirms what you guys already know. Don't go and take a multiple choice test where you have no idea what you're doing, because you'll have like a 96% chance of getting 8 or fewer of the questions right. So you've got like a 4% chance of getting 9 or more of them correct. I know this video is running really long. I'm hoping we'll get to these last two quickly. There is one more step of complexity that I can add, and we're going to find it right here. A player in a video game competition will be promoted to the next bracket if they win at least 3 out of their next 5 games. Player knows that they generally win 52% of the games that they play. Find the probability that the player is promoted to the next bracket. So if you're up for it, try at least the first few steps of this one on your own. I'm going to dive right into it here. Right? So step 1, we define the random variable. So I'm going to let G be the number of games out of 5 that a player will win if they have an individual win chance of 52%. Step 2, we state the distribution. G is distributed binomially with 5 trials and an individual probability of success of 0.52. Step 3, state the probability that I'm trying to find. Now it says that they want to win at least 3 out of their next 5 games, so they want to win 3 or 4 or 5 of them. Okay, so let's see here. I want to find the probability that the number of games that they win is greater than or equal to 3. We finally get to do something for step 4. We finally get to just think for step 4. So here's the thing, right? Remember that cumulative probabilities, the ability to do multiple probabilities on these things, always goes up to and including something. There's nothing on the calculator that will let me count from 3 up to 5. I have to start at 0 and go up to something. So step 4 is going to be where I say, the opposite of them winning 3 or more games would be them winning 2 or fewer games. So I'm going to do 1 minus the probability that the number of games they win is less than or equal to 2. Remember, they have to win some number of games, right? So this is representing that 100%, so I'm doing that minus the probability of them winning 2 or fewer games. Now this is something I can do with binom CDF, and then I just subtract it from 1. So in step 5, I can just work this out. So this winds up being 1 minus 0.463. And so I wind up here with 0.537. And that's our answer to the problem. Here's one last example so you can try it on your own. A 10-sided die is thrown 8 times. Find the probability of rolling lower than 4 at least 3 times. So I decided to go with let L be the number of times a 10-sided die comes up lower than 4 out of 8 throws. Step 2, I'm supposed to indicate the type of distribution it is. L is distributed binomially with 8 trials and an individual success of, let's see here, so rolling lower than 4, that would mean rolling a 1 or a 2 or a 3 on a 10-sided die, so that's 3/10 or 0.3. Step 3, I now indicate the probability I want. I want the probability that L, the number of times it comes up lower than 4, is at least 3. At least 3 times means it happens 3 times or 4 times or 5 times all the way up to 10 times. Okay, so I want this to be greater than or equal to 3. Okay. Step 4, do I need a step 4 here? I do, because this probability being asked for is not a less than or equal to. And so because of that, I'm going to need to shift it around. So the opposite of being greater than or equal to 3 would be being less than or equal to 2. And then in step 5, I just plug all of this stuff into the calculator using binom CDF. So I got this to be 1 minus 0.552, which means when I do 1 minus that, I end up with 0.448. There it is. There are other ways that these binomial problems can be more complicated, but we're definitely going to save that for another day. Congratulations on making it through this one. Remember, if you've got questions or you need some help, please let me know. You got this.